Okay, hi everyone, and welcome to the CLEX seminar for November. So it's my great pleasure to introduce our speaker for today, which is Dr. Paul Newman, and he's the Chief Scientist for Earth Sciences at NASA's Goddard Space Flight Center. And so I've known Paul through a number of ozone assessments, because Paul has been the co-chair of the scientific assessment panel for the Montreal Protocol on substances that deplete the ozone layer. And he, has been involved in the last 3 ozone assessments. Is that right, Paul? 3 or 4? 4 ozone assessments. So these ozone assessments are like IPCC assessments, but for the issue of ozone depletion, and they occur every 4 years. And so Paul's been instrumental in leading our community in trying to understand the Antarctic ozone hole and future, making sure that we continue to protect the ozone layer from depleting any further. So Paul has won many awards for his research, and he's also Vice President of the International Ozone Commission and past President of the Atmospheric Sciences section of the AGU. And he's kindly dialing in from his evening in Maryland. So thanks very much, Paul, for agreeing to speak to us, and I'll turn it over to you.
Thank you, Julie. Pleasure to be presenting. First time I was in Melbourne was in 1987, so right in the depths of the Antarctic ozone hole. So I'm really, I've been there now to Melbourne 3 times. One of my favorite places. I always, whenever I go to Australia, I have a lot of fun. It's a wonderful place to visit. So it's a little bit of payback on my part for being such gracious hosts. So let me just get going. Oops. I'm going to give you a little bit of an outline. What is ozone and why do we care? What's the threat to the ozone layer? How did nations act? The Antarctic ozone hole, and a whole bunch of things about the Antarctic ozone hole. And then I'll give you a summary. So some pretty basic stuff I'm going to start with here. First of all, let's talk about what is ozone. Before we do that, let's just talk about what air is. Most people know that nitrogen gas, N2, and oxygen gas, O2, comprise the majority of our atmosphere. There's various minor species. I put CO2 down there, which is up in the 420s parts per million now, but you can see that's actually a pretty tiny percentage. It's a very important gas, though. And there's ozone. Ozone in the stratosphere is a very, very tiny concentration of the overall atmosphere. And in the troposphere, it's even a smaller concentration. Now, ozone is a weird gas in the sense that it increases with altitude rather than decreases with altitude, as most gases do. Just to talk a little bit more about it, ozone is 3 oxygen atoms. And again, oxygen gas is O2, 2 oxygen atoms. They're pretty, as I already mentioned, concentrations are quite small. You get up to about 10 parts per million, up at around 30 kilometers or so. And ozone is mainly found in the stratosphere. I'll show a plot of that. Just to kind of give you a mass estimates, I figured I'd put the mass of the sun, the earth, the global atmosphere, and global ozone. So you can see, ozone is about 0.5% of the total global atmosphere, but it's a fundamental gas, as I'll show in a second here. Now, first of all, let's talk about the basic structure of the atmosphere. The troposphere down low is where all our weather occurs. The stratosphere, temperature increases in the stratosphere, and the mesosphere, temperatures fall off in the mesosphere. So the stratosphere is where we're really interested. Just give you some context to this. Your typical airliner flies at somewhere around 9 to 12 kilometers. Real high altitude plane like the old U-2 spy plane. NASA has 2 of these we use for atmospheric research. And I'll come back to this plane in a little bit. It flies at about 20 kilometers. That's pretty darn high for an aircraft. So now here's an ozone profile, and I've shown it in parts per million. And you can see that ozone increases with altitude up into the stratosphere, and then it falls off. Now, this is in mixing ratio. If you actually modulated it, if you looked at the density of ozone, if you look at the density of ozone, ozone actually peaks, the density peaks lower down. So 90% of the ozone is in the stratosphere, about 10% of the ozone is up in the troposphere, or is in the troposphere. So I want to talk just a second about units. I'm going to talk about the Dobson unit quite a bit. Dobson unit is just a convenient measure of the total amount of ozone between the surface and space. If we were to, and I just sort of show it in the cartoon here, you could bring all the ozone down to the Earth's surface. It would form a layer of gas about 3 millimeters thick. That's in the US, that'd be a couple of 2 pennies stacked on top of one another. It's not very much. Again, making the point, not a lot of ozone in our atmosphere. So why do we care? Back to my ozone profile here. So you can, again, I put a little sun up there. It's actually a very extreme UV image of the sun from Goddard. One of my colleagues gave me that. I mean, they do it every day, actually. And UVC, those are photons that are very extreme. They're below 280 nanometers. UVC does not get to the surface. If your eye was sensitive only to UVC, the world would be black. None of these photons get down to the Earth's surface. UVB, and this is what we care a lot about, this is between 280 and 320 nanometers. It's absorbed by the ozone layer. About 90% of it is absorbed. About 10% gets through. And then the third category is what we call UVA. UVA is both absorbed and scattered. About 50% of UVA gets to the Earth's surface. Now, most of the light you see, photons you see, are in the visible, detectable by eye. UV is not detectable by eye, but it is there to cause all sorts of effects. Now, I want to focus a little bit on plants here, and this is a picture I got from my colleagues, Nigel Paul and Janet Bornman. Growth is reduced if you increase UV, and it's increased if you can decrease the amount of UV. So plants and humans and other animals have repair mechanisms for UV damage. UV photons are energetic enough that they can break biologically active molecules. So if you have less UV, plants are not expending energy repairing themselves, they grow better. Similarly with humans, if you're not getting a sunburn, you're a healthier person. Now, just to continue on with this, we did a little experiment here at Goddard. I was going to try to show the movie, but I decided I better not show my little time-lapse movie here. What we did is we have a lab where we test satellite or materials for satellites, and we have a little lamp that produces a full solar spectrum. So we get the really hard UV photons out of this lamp that we don't see down here at the surface. I got myself a little boxwood basil and I set it up. I put a couple of detectors you can see over on the right side of that. Those detectors measure ozone and temperature. I have a little camera you can see on the left-hand side of this image. The camera, we put it in time-lapse mode, and then we turn the lamp on for 27 hours and expose this little boxwood basil plant to hard UV radiation. And this is what you get. This is after 27 hours. You know, you can see initially the bronzing of the leaves on this. They became shiny and kind of brownish. They were still, it wasn't like a leaf in fall that's dried out. These were tactile to the sensation still, you know, what was happening is the UV photons were blowing apart, you know, molecules in the leaf surface. We took the plant out of the lab and put it on a shelf and tried to revive it. I had 3 or 4 plants there, all of them these little boxwood basils, but this one died. You know, likely the reason it died is it's the equivalent of pouring an herbicide on it. It just made the entire plant, you're covering it with poison, or you're turning molecules into poisons. and the plant just died. So if you had no ozone in our atmosphere, these plants like this wouldn't be able to grow. They would die. And so it kind of gives you an idea. We talk a lot about sunburn, cataracts, but it's actually what might happen to plants that could be the most serious issue with excessive UV exposure because of depleted ozone. Now, I know that Australians with the Slip Slop Slap campaign are probably the world's most educated people on avoiding excessive sun. And so, yeah, we don't have anything like that in the US, but congratulations to Australia for doing this. I think it's a terrific campaign. I personally kind of abide by this, try to avoid the excessive sun. A little bit of sun is good for you to produce some vitamin D in your skin, but you know, if you're out there for a long time, of course, sunburns, skin cancer, cataracts, these are all adverse UV effects. So ozone is a really important gas to have to screen ultraviolet radiation. So let me move on now. Let me talk about the threat to ozone. So first I'm going to talk about two gentlemen here. On the left side is Rich Stolarski, and on the right side is Ralph Cicerone. And back in 1974, they published a study that said chlorine atoms can catalytically destroy ozone. And by catalytic, I mean the chlorine atom can regenerate itself to destroy another ozone molecule and regenerate and destroy another one. So one chlorine atom can destroy a few thousand ozone molecules. And these two gentlemen were the first to show this. Now, this was followed almost immediately by a paper by Sherry Rowland, who's on the left side of the picture, Sherry Rowland, who's on the right side of the picture, and Mario Molina on the left. And they published this paper that said chlorofluoromethanes could catalytically destroy ozone. So now they're looking at these compounds called, we call them chlorofluorocarbons, their ability to deplete the ozone layer. This is a really important study in sort of the history of science. If you look at the title, you can see the chlorine atomc-catalyzed. So the point being that they made a mistake in their title. Nevertheless, they won the Nobel Prize, so, along with Paul Crutzen. Unfortunately, both Ralph and Mario and Sherry have passed away, and Rich Stolarski, who is on the left side there, is severely ailing right now. So these giants of our field who actually got this whole issue kicking are now moving on. Well, let's keep talking about what was happening back then. So there were some early calculations after both the Stolarski and Cicerone and the Molina and Rowland papers that modeled. There were some very, very simple models, and they were modeling the impact of these CFCs on ozone. And you can see the figure on the right, which I took from a Steve Wofsy and Mike McElroy paper in 1974, almost immediately after the publication by Molina and Rowland, showing that in fact CFCs could lead to a large ozone depletion. So this was in 1974. So this 1976 report from the National Academy of Sciences used this figure and it discussed the potential for ozone depletion. So moving on from that, there was another document. This is the Stratosphere Recent Future. This is a NASA document, and this is published in 1979. And in fact, it showed three different scenarios here. The one scenario is where the release rates or emissions were fixed in 1975, and there was no release after the year 2000. And you can see ozone began to recover. The second one was the emission rates was fixed. And then the third one was where there was a 5% growth rate per year. And of course, there was a lot of ozone depletion from that. So back in the 1970s and early 80s, there was a lot of discussion about the impact of these chlorofluorocarbons on the ozone layer. Now, a few years later, it culminated in this giant set, which is really the forerunner of all of the ozone reports and the IPCC reports on climate. This 3-volume set on atmospheric ozone was published in late 1985, early 86, if you want to get technical. But this really was a international effort to say what was happening to the atmospheric ozone layer. The scientists coming together for the first time to really lay out the problem on an international scale. And it really was. You find everything in these 3 books, and they're just huge. But one of the main findings here, and I highlighted here, was the continued release of these CFCs would reduce ozone vertical column by about 5 to 8%, according to these simple models we had way back in the day, and about 9% globally. So these were really, really large losses. This was in 1980, end of 85 and 1986. So now on the political side, there were things that were going on. So how did the nations react to these findings by atmospheric scientists? So the first thing was I already talked a little bit about this tannish volume here, the stratosphere present and future 1979. There was another early WMO stratosphere 81 theory and measurements. So there was a lot of reports that were coming out. But on the top, I showed there was a WMO World Plan of Action on the Ozone Layer, which was 1977. So people were, the policymakers were starting to think about this very seriously. And that really culminated in 1985 with the negotiation of the Vienna Convention. Now, there are two agreements that I'm going to talk about. One is the Vienna Convention and the other is the Montreal Protocol. So the 1985 Vienna Convention did 3 things. The first thing, it recognized that we needed to protect the ozone layer. So countries were convinced we had to protect the ozone layer. This is a big issue. It's hard to get countries to agree on anything. And here they agreed to protect the ozone layer. The second thing is they actually established what's called the Ozone Secretariat, which is part of UNEP now. And the Ozone Secretariat was organizing regular meetings for ozone layer issues amongst policymakers from different countries. Also, amongst the scientists, they established a framework for science research. And that framework for science research still goes on to today. Every 3 years, the ozone research managers meet to outline studies over the coming years. So there's the atmospheric ozone, which came out in 1985, just followed the Vienna Convention by a little bit. But then in 1987, so the policymakers read that big 3-volume set, and they decided they needed to act. That the science was solid enough. We weren't seeing a lot of ozone depletion, but they decided the science was solid enough that they were going to regulate production and consumption of certain compounds that could impact the ozone layer. That was a real remarkable achievement. It also established a multilateral fund, which has regular reporting from countries goes to the multilateral fund. And they re-examine control measures every year. They also receive money from countries to help developing countries get rid of CFCs and hydrofluorocarbons. But the Montreal Protocol also formalized the scientific assessment panel. So the writing of these, like the blue volumes there, the writing of these volumes was actually put into an agreement. So there is now a science assessment panel as part of the Montreal Protocol, and that's what I have served on. I was co-chair from 2007 to the present, and I have just recently resigned my position there, and somebody else is going to take over. But I also was part of the assessments that preceded that all the way back to 1989. So I've been doing these assessments for quite a few years now. And I put in here parenthetically that the Vienna Convention, the Montreal Protocol, are not specific parts of the UN. They don't come out of the UN. They are their own agreements. Okay, they exist on their own. The parties are assisted by this Ozone Secretariat, which is part of the UN environmental program that was headquartered in Nairobi. But the two agreements exist on their own. So let me talk a little bit about the 1987 Montreal Protocol. It regulated 8 different ozone depleting substances. I call them ODSs. And the thing of this agreement, the first step in 1987, it didn't stop production and consumption or emissions. It just slowed it. And in fact, if you look at what we expected way back in 1987 and what the Montreal Protocol was supposed to do, it didn't stop the growth of chlorine and bromine compounds. It only slowed them down, or slowed the emissions down. So it as a first step, it was great, but it didn't actually stop the growth of CFCs in the atmosphere. Now, I'm going to jump into the Antarctic ozone hole because this appeared at about the same time. All these negotiations are going on, these agreements are being written, and this thing called the Antarctic ozone hole popped up. So let me go into that a little bit. First, I want to talk about the discovery of the ozone hole. So the ozone hole was discovered by these 3 gentlemen. On the left there is Joe Farman, in the middle Brian Gardner, and on the right John Shanklin, and they're standing in front of a Dobson spectrophotometer. These are ground instruments, and they look up and they measure the total amount of ozone overhead. And the black points that you see here are actually those observations in 1984. Now I'll get to the blue points and the magenta points in a minute here, but the black points are the actual observations. Now this was followed by this gentleman you see down here on the right. His name is P.K. Bhartia. And there was a huge room full of computers that made this image. This was the first image of the Antarctic ozone hole there in the center, kind of in an orangish color. And now I'll go back to the magenta points, and the blue points are the values of total ozone at the lowest point during October. Now, you can really see that through the 1960s, 50s, 60s, and into the 70s, ozone was sliding downward very slowly. But in the early 1980s, it started going down fast. Both the satellite instruments and the ground instrument at Halley Station showed this precipitous decline. Now, I actually arrived at NASA Goddard in 1984, and this was one of the things people came to me and they asked, well, what do you think of this? And it was a puzzle. It was mystifying how ozone could drop so quickly. In a lot of ways, it was kind of frightening. You knew that the observations were good enough that there was no question that this was a real trend. And so this is actually a bit frightening. Now, let me show you a couple of pictures. I'm going to go on. Actually, new color images that I made. This shows the picture of ozone over Antarctica on the top there in 1979 and the picture in 1984. So you could see that this low bluish area that you're seeing, it's not a small thing. It's continental in scale. It's a huge phenomenon. It's not located over one station like the black points show. It's continental in scale. So now I'm going to show you our estimates of chlorine over Antarctica, and I partitioned it into various compounds here. This was the Joe Farman paper, the discovery of the ozone hole paper. They hypothesized that CFCs were causing the ozone hole. And from the lower picture, these are amounts of chlorine above Antarctica in the stratosphere from the various compounds, and you can see that there's a couple of natural compounds in there, methyl bromide and methyl chloride. They're the kind of purplish colors. But other gases like CFC11 and CFC in purple and CFC12 in pink were increasing rapidly at the time of the discovery of the ozone hole. Also carbon tetrachloride in dark blue. And there are a number of other minor CFCs that were going up. And you could see that the amounts were increasing exponentially. So this was in 1980. This was in 1984, that 1985 that we're looking at pictures like this, and people are wondering, well, maybe there really is. Maybe the ozone hole is caused by chlorofluorocarbons. So that was the picture in the 1980s, or in the mid 1980s. What was caused? We knew ozone was going down fast. We didn't know what was causing it. It was hypothesized that it could be CFCs. Now, so what's causing the ozone hole? So now I'm going to do a little bit of a deep dive to try to explain what's going on with chlorine getting down over Antarctica and causing the ozone hole. Now, I don't want to give you the idea there were no other theories. There were other theories, and I'll remark on them in a minute or two. But I first wanted to show one of the theories that came out back in the 1980s, that the UFO aliens were down there stealing our ozone layer at the South Pole. It's a wonderful picture of ET. I'm sure that if the aliens were here, they'd look just like ET. Okay, so let me move along here. So I just put this in bold statement here. The chief causal factor of the ozone hole is the high levels of chlorine and bromine over Antarctica. Now, in the background there, I have a picture. It's a zonal mean, so you average in longitude. So you get a pole-to-pole picture and a picture in altitude of CFC12. Now, the first thing you note is that CFC12 is high down in the lower atmosphere. You can see the scale on the left from 0 to 64 kilometers. CFC12 is pretty high, and the red colors indicate high amounts, and it's higher in the northern hemisphere than in the southern hemisphere. And that's because most CFC12 is being released in the northern hemisphere. So what happens is that CFC12 is released in the troposphere, as I remarked. We used to use it in car air conditioners. So it was also a really good solvent. You could clean automotive parts really well with CFC12. And it's carried into the stratosphere in the tropics by this slow rising circulation. Call it the Brewer-Dobson circulation, but just keep in mind, there's this big lifting motion in the tropics, and it comes down in the extratropics. So we call that the Brewer-Dobson circulation. And in fact, you can see the CFC12 bows upward because of this lifting motion by the Brewer-Dobson circulation. Now, as it begins to get higher, it actually gets above the ozone layer, and the CFC12 can be photolyzed in the stratosphere by intense solar UV, and that releases the chlorine that is in CFC12, okay? And CFC12 is 2 carbons, 2 chlorines, and 2 fluorines. So the 4 bonds of a carbon atom are bound by the fluorines and chlorines. So it's being photolyzed in the stratosphere, and it's releasing chlorine. Now, that chlorine catalytically destroys ozone. There's a specific catalytic cycle, and it eats a couple of thousand ozone molecules when it's up there. Now, eventually, the chlorine reacts with methane or NO2, and it forms 2 non-reactive species, HCl or chlorine nitrate. Now, this was really pretty well understood back in the 1980s, that the chlorine would destroy a little bit of ozone, but when it came down, it would form these 2 non-reactive HCl and chlorine nitrate, what we call reservoir species, but they're not ozone-depleting agents. But we knew there was polar ozone depletion down there. So that brings us to the next thing. HCl, chlorine nitrate, they're reservoir species, non-ozone reactive. So how do we get ozone depletion over Antarctica? Remember, Farman and Gardner and Shanklin hypothesized that the CFCs were doing this. If you go back and you read the Farman paper, you actually, as you read through it, you recognize that it's missing something. It doesn't get the chemistry right. That was also recognized pretty well back in the mid-80s. So here's a little mystery element that actually solved the ozone problem. It's a picture of a polar stratospheric cloud. These are clouds that form in the really dry stratosphere, and they're beautiful clouds when they're seen from solar scattering here. This is the actual color of these clouds. They're called the mother of pearl clouds also. This was a picture I took in January 14th, 2003, 20 years ago almost. Well, more than 20 years ago now. And these are the key to the Antarctic ozone hole, and I'll explain that. So let's start off with this. I got a little cartoon polar stratospheric cloud particle here. And this is Susan Solomon, Steve Wapsie, Mike McElroy, Paul Crutzen, and Arnold. They suggested there could be reactions on the cloud particle surfaces. to activate chlorine. And in fact, they were right. The HCl and the chlorine nitrate react on the surface of a polar stratospheric cloud, and they leave behind nitric acid and they release chlorine gas, Cl2. Okay, now Cl2, chlorine gas is easily photolyzed by just regular sunlight. It doesn't need UV radiation. It just needs a little bit of sunlight. And so now you release those 2 chlorine atoms to catalytically destroy ozone. Here's the catalytic cycle, but I don't think you have to pay a lot of attention to this. Just pay attention to the fact that you start on the left side with the chlorine and 2 ozone molecules. And on the far right, you've got 3 oxygen atoms and 2 chlorine molecules or chlorine atoms that you got back. This is the catalytic cycle, and this repeats itself over and over and over and over again. And in fact, ozone is depleted by about 1% per day over Antarctica. Now, this was the theory back in 1987. And in fact, there was a NASA and NOAA sponsored what's called the Airborne Antarctic Ozone Experiment in 1987. And they used that U2, the NASA U2 that I mentioned at the start of the talk to go down there and look for these chlorine reactions. So I'm going to show you the measurements and take a look at the dates. This is August 23rd, 1987. This is when the Montreal Protocol was being negotiated, and they were making these measurements. The blue line shows CLO. This is one of the molecules involved in the catalytic destruction of ozone. And the red line shows ozone. Put the ER2 in there just to give you an idea what it looks like. And this is on September 16th. Now, this plot on the right is called the smoking gun plot. And if you look at it carefully, you can see that where ozone, or excuse me, CLO, chlorine monoxide, is very high, ozone is low. And in fact, they're anti-correlated. So high chlorine monoxide leads to low ozone. And in fact, if you make the calculation, it comes out just about perfectly from the chemical kinetics. So we knew that the chlorine was being the chlorine was eating ozone. In fact, the only way you get up to these very high concentrations of CLO is from man-made species. So we also knew that it was man-made species that were doing the job, these CFCs. Okay.
10:35, Paul.
Okay. All right. Let me move along then. I'm going to really quick go through this to just sort of give you an idea. This is temperature in the lower stratosphere in the Antarctic. And you can see polar night starts and the temperature begins to fall off. It's almost like it hits a little edge and starts heading downward there. Polar stratospheric clouds begin to form when you get down to about 195 degrees Kelvin. And there's a long period in which those clouds are there, and the HCl and chlorine nitrate can react to release chlorine gas, and nitric acid. It is polar night in the middle of the winter, so you don't have sunlight to break apart the Cl2, but eventually the sun comes up. Here's a picture of sunrise down at South Pole Station. And then you begin to get, you break up the Cl2, you get rapid catalytic ozone loss. And eventually the temperatures warm up and the polar stratospheric clouds go away. And the vortex breaks up and it mixes, we form an ozone hole, and it mixes all that ozone depleted air all over the southern hemisphere. Bad news for Australia. So the recipe is, if you get cold temperatures, those will form the PSCs. You add in to your chamber there a lot of chlorine, you get heterogeneous chemical reactions, and that leads to a large catalytic ozone depletion. That's the basic theory of the ozone hole. Cold temperatures, PSCs, high chlorine, a lot of depletion. So let's move along. What's happened since the discovery? Well, first of all, that graph I showed you ended in 1987. The amount of chlorine was heading upward exponentially. The Montreal Protocol was signed, and in fact, the amount of chlorine over Antarctica peaked out in about the year 2000. So that's good. Chlorine was going up, and now it's topped off and it's falling off. I should also add that every nation has now signed the Montreal Protocol and the Vienna Convention. 198 countries. Imagine all the disagreements you see today around our world. but all of these countries have actually signed this agreement. So if I look at this, levels of chlorine over Antarctica have actually fallen about 31%, down to 31% down to the 1980 level, not all the way back to the 1950s. And in fact, I talked about these assessments. Now here's the big lineup of all the covers of these assessments. They continue to be written. The last one on the far right there was published just a couple of years ago. And so what's happened? The Montreal Protocol evolved. I showed you the plot where there was no Montreal Protocol, then there was signed, then another amendment was added in London, then another amendment was added in Copenhagen, there was another amendment added in Beijing, and now we can see where the future is that gray line down there. Chlorine compounds went up, and now they're falling. So the Montreal Protocol has worked. Chlorine compounds measured in the atmosphere are declining. All right, let's head off to the ozone hole. So I showed you the picture initially of the Halley Station observations and the satellite observations together. And here you can see what they look like now, all the way to this last October. So you can see that it got pretty bad. It got about to its worst in the mid-1990s. And there's kind of a hint of things going upward. Now, this is the measurements I'm showing. The black points are the Halley Station observations, and the blue points are the lowest value inside that October. So it's where you see those purplish values in 2006 and 2023. It's those low values that I'm plotting as the blue points. So I'm going to talk about a couple of metrics here. Again, these are all in Dobson units. So I went through that little exercise of Dobson units. And greenish is the 3 millimeters thick level. Blue is a very thin kind of a dime level of stuff. So I'm going to start by talking about the lowest values here. These are for 4 different days in 4 different years, all on October, well, same day, October 4th, and 4 different years. So you can see how the ozone hole is getting bigger, and the area, the line enclosed by the white line, that's the 220 line, is getting larger also. So we look at the ozone hole from a depth, what's the lowest value we see, and we also look at it from an area viewpoint. How much area is enclosed by that 220 value? So that contains, you know, if it's a really big value, then the ozone hole is really large. So now let me jump. Here's the ozone areal coverage as a function of year. Now, pay attention to the black points. Those are averages. This is a September to mid-October average. So we take all the points. The gray bars are just the range of values that go into the average. You can see there's it was climbing upward in area into the 1990s. And now it's this last ozone hole is 23.1 million square kilometers. So to give an idea, the area of the entire North American continent is almost 25 million square kilometers. So this is a big thing. This is the size of North America. Here's the daily minimums. What we do is we take the daily picture and we average all the minimums together for the different years. Again, the gray bars are the range of values, not the standard deviation, the range of values. And you can see that 115.1, that makes this, this year was the 20th deepest. As I mentioned, I think I said it, but the 23 ozone hole was the 16th largest in area, and it's the 20th deepest in the minimum value. So I'm going to show the same picture, but now I'm going to show you a line that's a straight line fit from 1999 to the present. And you'll notice there's a couple of really high points. In fact, those are 2002 and 2019. We know why that happened. These were what we call warmings. These were weather events that occurred in the stratosphere. If we take those out, we do get a statistically significant increase. We have to take out 2002 and 2019. So it is statistically significant and going up about 1 Dobson unit per year. The area is also falling. Here you can see the area is getting a little bit smaller, but it's not the downward trend is not statistically significant. It's a slow downward trend. Now, one of the things I've done here is I've colored the temperature of the lower stratosphere with reds and blues. So really cold years are the blue points and the really warm years are the red points. So you see the red points, the dark red points those really, really small ozone holes. The blue points are the very large ozone holes. So there's a temperature factor that goes into this, and I'll get to that in a minute. So one of the main factors that control the severity. So I'm going to show you a picture of the area. Again, this is the area of the ozone hole. It's an average September 20th to 30th. And again, you can see that really small ozone holes in 2002 and 2019. And then the blue line is what I've done is I know that chlorine and bromine cause the ozone hole. So what I've done is I've just taken the chlorine and bromine levels and I fitted them to the area, and that's what the blue line is. Okay, the blue line is just a chlorine and bromine fit of the areas right there. So we already know this, that chlorine and bromine explain the very broad trends that we've been seeing. Now, what I can do is I can look at the residuals here. And here I showed the residual for 2019. It's quite big. It's much smaller ozone hole than we would have expected. We would have expected something around, 20-something million square kilometers, and we got something less than 10. A big deviation in the year 2019. Now, if I subtract, I take the black points and I subtract off the blue line, I can get an ozone area anomaly. Okay. So this plot shows those anomalies on the y-axis versus the temperature of the lower stratosphere on the x-axis. And you see here, it's a really nice straight line. And so I showed previously that area with the red points and the blue points. Well, this shows it in a pretty good statistical way. This very, very nice straight line. And they're kind of in the middle, grouped all together here is the 2023 value. It's a little bigger than normal because it was just fractionally colder than normal, but in the middle of the pack. Now I can actually, I fitted the area with chlorine and bromine. I can use this line here, this ozone temperature relationship, to fit the ozone area again. And that's the red line that you see. So there's the same ozone areas that I've been showing. And here's the red line fit if you fit with both chlorine and bromine and with temperature. And you get a pretty good fit here. So the basic point is that halogens and the stratospheric meteorology largely explain the severity of the Antarctic ozone hole. Now, I didn't want to leave you cold about Hunga Tonga because that's been a big topic people have talked about. So I'm going to show that really quickly. This is a couple of water vapor plots from Hunga Tonga. On the top is just vertical profiles from the MLS instrument. MLS is on the ORIS satellite, shows water vapor. And I subtracted off a time mean here. The top plot shows the equator. So it's a function of altitude and year. And on the bottom is the same thing from MLS, but it's at 75 degrees south. Now, the red line shows when Hunga Tonga erupted. And you could see that there's a huge amount of water that suddenly appears in the stratosphere right after the Hunga Tonga eruption. And in fact, the Hunga Tonga eruption increased the total amount of water in the stratosphere by about 10%. So when Hunga Tonga went off, we began to worry what's going to happen with the Antarctic ozone hole. Is it going to have a big effect or not? So let me kind of walk you through it. There's the plume extended well into the upper stratosphere and tropics shortly after the eruption. You can see this is up at 25 kilometers or so. And the plume just kept going up in the tropics. It's just this normal upward, where I talked about this Brewer-Dobson circulation, rising air in the tropics, air descending in the extratropics. So here you see, this is a plot of water vapor, and it shows the rising air in the tropics. And in fact, you can see the alternating dry and wet air, but the Hunga Tonga plume is going up in altitude. And this plot here is current, actually. So you can see there's a lot of water up high from Hunga Tonga. It appeared you can see that it went off, but none of that water got into the polar vortex over Antarctica, where the Antarctic ozone hole is, in the year 2022. But when the ozone hole broke up at the end of 22, all of this high water air in the middle stratosphere mixed over Antarctica. So last year at this time, we knew the breakup was coming. In January, February, March, we knew there was a lot of water over Antarctica. We thought it might have an impact. And in fact, you can see that a lot of that water was just frozen out. It gets so cold over Antarctica that you freeze dry all of this air. And so it's kind of a normal process that we see every year. You can see the previous years, you see this big dry striping stuff coming down. Again, that's the downward branch of this brewer topside, rising in the tropics, sinking in the extratropics. So here's an ozone picture. This is from a model projecting out. So you see this model, and it said that it'd be enhanced Antarctic ozone depletion, 20 Dobson units in 2023. And you can see that as the water comes out of the stratosphere, this signal decreases as a function of year. Not much going on in the northern hemisphere, a little bit of depletion, but only a few Dobson units in the Arctic. So it turns out that because there was nothing in the Antarctic in 2022, we didn't see much in the way of anything. And we expected 20 to 25 Dobson units of depletion, enhanced depletion over Antarctica. But the year-to-year variability of the depletion is about 33 Dobson units. So the signal we were going to get from Hunga Tonga is about 2/3 of the signal that we see in year-to-year variability. So Hunga Tonga was going to be hard to detect. And in fact, while there were some hints of some additional depletion in 2023, this depletion was really not significant. So where are we headed? So this is a model simulation of the ozone hole. You can see the 1971 level, 2006 when things were pretty bad. And you can see things improving as we go out to the future. In fact, with some recovery in the 2060s, 2070s, back to the 1980 level. Now, climate is probably going to have some impact on the ozone hole, but not a lot. I show actually 3 pictures here. On the top is chlorine and bromine. They continue to go downward. You can see ozone was depleted annually. This is the partial global average, 60 north to 60 south. We exclude the polar regions. And you can see 3 different scenarios here, one with a lot of climate gases, CO2, N2O, methane, moderate amount and low amounts of greenhouse gases. And then down on the bottom here is the Antarctic ozone hole. You can see there's only in the most extreme CO2, methane, N2O cases is there an effect in the Antarctic, but it's mainly going to be the ozone hole is largely unaffected by greenhouse gases. So we expect the ozone hole to be better in the 2060s period. So let me kind of summarize. So ozone is one of the key gases in our atmosphere that screens harmful UV radiation. The Antarctic ozone was discovered in 1985 and was found to result from chlorine and bromine compounds that are mainly human produced. Like I mentioned, Joe Farman, he got the idea right, he just didn't get the chemistry right. So mainly he gets credit for having discovered it, and he was the first to really hypothesize that it was CFC. The third point here is that the 1985 Vienna Convention and the 87 Montreal Protocol are flexible agreements that have led to strong controls on ozone depleting substances. All 198 of the world's nations have signed these treaties. The ozone hole is not getting any worse, and we're now beginning to see the first signs of recovery. And finally, as I just mentioned, the Antarctic ozone hole will be back to 1980 levels in the 2060 to 2080 period. So thank you for your attention.
Thank you, Paul. Fascinating. So we now have time for questions. We have 8 minutes for questions. So please either raise your hand using your actions button, or you can even shout out if you want. You could also put questions into the chat if you want to. I'll get things going by asking Paul, to what extent do you think the success of the Vienna and Montreal protocols were actually assisted by technological developments that came up with good replacements for CFCs? We used to use it as refrigerants. They came up with something else that wasn't as damaging. It's like, was that a key piece of the puzzle for it succeeding the way it did?
That was a piece of the puzzle, but I think it's a little bit of a myth to say that was key. There was, at the time the protocol was signed, most processes, it was unknown if there were replacements for a lot of these processes. Remember that the use of CFCs was increasing pretty fast. And there were many products. So the protocol actually, first of all, there were technologies, but the protocol is set up with what's called the Technology and Economics Effects Panel, the TEEP panel. And they work quite hard to find alternative technologies that could be used to replace CFCs and HCFCs. And so that was a fundamental part of the agreement that was successful. The multilateral fund was a big part of it also. The ability to actually fund efforts to get rid of CFCs was a huge innovation. There was also an element of luck, I think. It was in the US, it was Ronald Reagan who signed the Montreal Protocol, a very conservative politician. And in the UK, it was Margaret Thatcher who signed for the UK. So now I'm not sure that there would be the political will on the right, at least in the United States, to deal with CFCs. So in some sense, we were a little bit lucky. So there was a number of elements. I think it also had to do with good science that went into showing that these actions were really needed. So I think there's a few things that happened that were really part of the success of the protocol.
Do you see things that happened with the Montreal Protocol and the Vienna Convention, like you mentioned one there about some fund to like come up with alternatives that you're not seeing in our battle to reduce CO2 and other greenhouse gases?
Well, first of all, let me say that CO2 is a few orders of magnitude larger than the Montreal Protocol or the CFC issue. Okay, so there's a scale here. And the other thing about CFCs, we did transition from chlorofluorocarbons to hydrochlorofluorocarbons, which are much less ozone depleting than CFCs, but still ozone depleting. And then they transitioned to hydrofluorocarbons, which have virtually no ozone depleting effects. So that was important, but the very companies that produced those compounds were the companies that would produce the alternatives. For things like CO2 and natural gas or methane, those companies are not the companies that will produce. They could produce new alternative energy technologies, but generally aren't. So there's like I mentioned, an element of luck there, but also, people who were visionaries that were prepared to transition.
Well, we have a question from Julie. You.
Yep. Hi, Paul. Thanks for that. It's such a positive story, I think, of science informing policy and actually being successful. And I guess I wanted to ask where you feel the science is needed now in terms of this issue, or whether it's all solved, or if there's kind of mysteries that we still don't understand, or I guess the role of monitoring to make sure that there's not new substances that might destroy the ozone layer.
Yeah, good question. So, like I mentioned at the start, there's a few fundamental gases. We all need oxygen to breathe. CO2, we talk about excessive amounts of CO2, but CO2 is actually a pretty key gas in our atmosphere to keep the surface warmer than would occur if there were no CO2 at all. But ozone is one of those fundamental gases for screening ultraviolet radiation. Life at the Earth's surface couldn't exist if we didn't have an ozone layer. That means we have to be vigilant about all processes that might affect the ozone layer. We've talked about chlorofluorocarbons in a major way, but also what about rocket launches? Rockets. I mentioned the original Stolarski and Cicerone paper. They thought the source of chlorine for the stratosphere would be shuttle launches and solid rocket boosters. So we have to keep an eye on rockets, satellite debris coming back down through the stratosphere, other species that are being produced on an industrial scale. There are minor CFCs that are now reappearing in our atmosphere. So there is a really great need for vigilance. I should also remark that we were well prepared to understand what Hunga Tonga, to follow Hunga Tonga, because we do have a very active and engaged scientific community that pays attention to these issues. So there's still a need to measure all these gases. In fact, all the CFCs, there isn't a single South American station measuring ozone depleting substances, hydrochlorofluorocarbons or hydrofluorocarbons. It's like unknown territory there on measurements of that sort. There are very few measurements in Southeast Asia. One of the golden stations of the world is down at Cape Grim. That is the big sole Southern Hemisphere middle latitude station. And thank God we have it, because it keeps an eye on what's happening in the Southern Hemisphere. And it's really key to the science, understanding mixing rates between the gases between the Northern Hemisphere and the Southern Hemisphere. There's a lot of these new gases, CF4, SF6, that are now, which have huge lifetimes in our atmosphere, and have been steadily rising for quite some time. So there's a lot of vigilance we need to pay attention to, but also new things, new supersonic transports are being built. I already mentioned rockets, but debris from satellites coming back down through the stratosphere. It's a recent paper on that. So there's a great need for vigilance, because of course, ozone is such a fundamental gas in our atmosphere.
Thanks so much, Paul. We've come to the end of the hour, and so you'll be moving over to the early career researchers section. Jara has probably set you up for that already, but can we all please thank Paul again for not just a great talk, but also for the great work you've done over your career in keeping everybody's eyes on this and helping it move along. Huge contribution, Paul. Thanks so much.
Thanks, Greg.
Thanks, Phil.